So in this particular example, we're going to go back to the two-dimensional potential method of mirrors, and we're going to see how that really works with the flow around the cylinder in 2 dimensions. So in the case that, consider the following case. You got a two-dimensional cylinder of diameter d, so that means your radius is equal to d over 2, and the height of this wind tunnel, the total height is h, and you have a uniform flow that's actually going all the way through. Okay, so what really happens is we are many times interested to know what the velocity is here. So as I was saying, we are interested to find what the stream velocity is here and any other location. So in order to do that, the best way to do this is using the method of mirrors. Because what we want to do is basically we want to find an expression. We would like to find an expression for ES. Okay, you may want to take a pause and maybe take a screenshot of this whole thing. And basically, A is the apparent free stream velocity experienced by the cylinder. If we want to find that, what we do is we say this is 1 plus something else, and we want to find that something else in this expression. Okay, and we want to find that in terms of d, h, and your velocity v. We don't know what the velocity could be. This is done very often, and it's called the solid blockage correction factor. And we do this a lot, especially for wind tunnel testing, to actually model this kind of problems. Okay, so to do this, let's go and consider the following. So basically what we are trying to do is we are trying to take your cylinder, and remember your cylinder is nothing else than a doublet, right? So what we are doing is we are generating a bunch of doublets, infinite doublets, because of the mirror, because this is a wall. So since it's a wall, I can keep duplicating this n times, and the distance from one doublet to another is h, and the distance from here to there is h as well. And what we know in our problem is the following. So we know that your total your velocity, let's say u theta, will equal to minus v infinite times 1 plus a squared r squared sine of theta. And if you want to evaluate all of this, let's say at theta equal to pi over 2, or let's take 3 over 2 so we get rid of this minus sign. So if I did this, then your expression basically, and then you had the VR as well. You had this other expression here. But I don't care so much for that expression, because what happens is this is multiplied by cosine, and then cosine of this will actually give you equal to 0. Okay, so the total velocity then ends up being just, remember, your velocity is the ur squared plus u theta squared. So since we are squaring and this is going to give you 0 at this location, then I really don't care. Okay, so if I did that, then your total velocity now at this location will be 1 plus d over 2, remember that was my radius, over your r. We work with the r in a minute. So your r is actually equal to nothing else than square root of x squared plus y squared. And note that we are located right here in the middle, right? This is where we are locating everything into, and this is x, this is y. So you're changing in y, but there nothing is, we want to do everything x equal to 0. So x is equal to 0, and then this gives you equal to y. So r is equal to y, so this whole thing down here is equal to y squared. Okay, so your entire expression now, actually, if you look at the problem carefully, and knowing that we have infinite number of y's, then this is actually, the second expression becomes as follows. Your total v is is V plus D over 4. Then you had V infinite, and then you have N times H, okay, squared. So what you had, this is squared, sorry. And since this is N time, your N has to go from minus infinite to infinite, and just note that N cannot be 0. Okay, so we skip that value. All the other values are actually included in this summation. So if I did that, then your whole expression becomes V infinite plus V infinite D squared over 4H squared, summation of N equal to minus infinite to infinite 1 over N squared, N different from 0. And this expression right here is actually equal to pi squared over 2. Okay, so just give me a moment. This is okay, that's what the expression is equal to. So now, using symmetry, because this is not actually equal to 0, and it's symmetric at the top and at the bottom, then what we can do is this is same thing as 2 times summation of N equal to 1 to infinite and 1 over N squared. Okay, N has to be an integer. So this is what we do, and this expression right here, we know for a fact this is equal to pi squared over 6. This is a nice, neat mathematical closed form solution for this infinite series. So if I did this, the whole expression then is nothing else equal to V infinite, and you can write it as 1 plus pi squared over 12 D squared H squared. And if we compare this to what we had, I'm sorry, this is not V infinite. Okay. Then if you compare what we had before, this is at any location A. So then this expression right here actually gives you the value of E of S that you were looking for. So for this E of S, you can see that this E of S in the most general sense will actually is a function of D and H, but it's a function of V as well, because if you look at it, multiply all the terms, then that becomes V infinite times, and the V infinite is multiplied by this term right here. Okay, so this summarizes and concludes example number 2 on flow around cylindrical cylinders, using also what happens in a wind tunnel testing.